So far we have discussed application of method to find complementary function for homogeneous partial differential equation. Now we discuss a trivial theorem, slightly trivial or a simple theorem related to solution of homogeneous partial differential equation like complementary function and particular integral. So this theorem states that if u1 is a particular complementary function of partial differential equation f dx comma dy z is equal to 0, and u2 is a particular integral of f dx comma dy z is equal to rxy, then to show that sum of u1 and u2 will also be solution of the partial differential equation. Now since u1 is solution of this PDE, so this u1 must satisfy this relation on replacing z by u1. So that is f dx comma dy u1 should be equal to 0. So we label it as by number 1, and u2 is solution of f dx comma f dx comma dy z equal to rxy. So z can be replaced with u2. So we obtained f dx comma dy u2 equal to rxy, right? And we label it as equation number 2. We can simply add these two equations to arrive at this relations, which actually proves that u1 plus u2 actually satisfy our partial differential equation, and this proves our theorem. Now we will discuss how the complementary function is written in previous discussion, right? So we consider a partial differential equation in general format, and we call it as equation number 1. And for complementary function, we replace rxy by 0, and we name it as equation number 2. Since f dx comma dy is a polynomial in dx and dy, so we consider it as a nth degree polynomial, homogeneous polynomial in dx and dy of degree n. Right? So our PDE can be written as like this, and we label it as equation number 3, where first coefficient an shouldn't be equal to 0. Now it is always possible to factorize this expression, because it is an homogeneous polynomial which is always factorizable by fundamental theorem of algebra, right? So we can write this expression as a product of linear factors like dx lambda 1 dy, dx lambda 2 dy, and so on, dx lambda and dy z is equal to 0. And this factorization, I must say, always possible either in real domain or in complex domain, where lambda 1, lambda 2, lambda n are all distinct constants. They may be real or they may be complex as well, right? Now we will proceed with the replacing dx upon dy by lambda in equation 4, right? So we will obtain a relation like this, right? We will take dy common on both sides. Like if we take dy from this factor, if we take dy common from this factor, and this factor, and so on, we will obtain a relation like this, right? And if we replace dx by dy, dx upon dy by lambda, then we can obtain the an equation or expression like this, which will be factorized into a naught lambda minus lambda 1, lambda minus lambda 2, and so on, right? By assuming lambda 1, lambda 2, lambda n to be roots of this expression, we can equate it equal to 0, and this equation will be called as auxiliary equation for a given partial differential equation, and lambda 1, lambda 2, lambda n will be its roots. Now we discuss two different cases, and we start with case number 1, when all the lambdas, that is, which are roots of this auxiliary equation, are distinct constant, right? Now clearly we can see that from equation 4, that is whenever this factor equal to 0, this whole product will be equal to 0. That is a solution of this factor will be solution of whole product, right? That is a solution of every of these factors will be solution of original differential equation, right? And we start with the first factor, that is dx minus lambda 1 dy z equal to 0, and writing dx as curl upon curl x and dy as curl upon curl y, we obtained an equation like this, which is obviously a Lagrange's equation of the type capital P capital Q is equal to R, right? And here R is equal to 0, and the Lagrange's auxiliary equation will be written like this, that is dx upon coefficient of this, and dy upon coefficient of this, and dz upon, which is dz upon 0, right? And z is your dependent variable. These equations can be easily solved, like this can be easily solved to give z is equal to a1 being a constant of integration, and by taking first and second we can arrive at y plus lambda x equal to a2 is another arbitrary constant of integration, and there must be a relation between a1 and a2 through some arbitrary function phi1, right? And we can write a1 is equal to phi1 of a2, or we can obtain z is equal to phi1 y plus lambda 1 x, because a2 is our y plus lambda 1 x, right? So this will be the one of the solution of our original equation 3, and similarly for lambda 2, lambda 3, we can obtain solutions like this, z is equal to phi 2 y plus lambda 2x, and so on, z is equal to phi and y plus lambda x, and so on. And adding all these solutions like this and so on, we can arrive at our complementary function. Now the second case is when one root is repeating. For example, we take lambda 1 and lambda 2 as equal roots, that is lambda 1 is repeating root or lambda 2 is repeating roots, and the rest of the other roots are non-repeating and they are distinct, right? And corresponding to, obviously as discussed in previous case, corresponding to lambda 3, lambda 4 and so on, lambda 1, the solutions will be like z is equal to phi 3 y plus lambda 3x, z is equal to phi 4 y plus lambda 4x, and so on, z is equal to phi n y plus lambda n x, and so on. And we left with the discussion of the solution corresponding to lambda 1 and lambda 2, which are equal roots, right? And corresponding to lambda 1 and lambda 2, we equate them to a common number lambda, and we see that we can observe that in equation 4, that is this equations, these two factors can be multiplied together, because this lambda 1 and lambda 2 are equal. These two factors will give us a single factor, like dx minus lambda dy square equal to 0, and solution of this will also be solution of our original partial differential equation, right? Out of these two factors, we equate one of the factor equal to b, right? So phi becomes, the equation phi became dx minus lambda dy v is equal to 0, which is obviously a simple Lagrange's equation and can be easily solved to give v is equal to psi y plus lambda x, right? And psi 1 is again our arbitrary function, right? And we can replace this v in our equation 5, right? And we obtain another partial differential equation of this type, which is again a Lagrange's equation, first order Lagrange's equation, and it's a Lagrange's equations are dx upon 1, that is coefficient of dx, and dy upon lambda, right? And dz upon our that is your r, capital R, right? Because Lagrange's equation, as we know, can be written as pp q equal to r, right? We can solve these two equations, right? First two fractions can be solved to give lambda x plus y equal to a1, right? And we can solve these two first and last equations by replacing y plus lambda x with a1, right? And we see dx upon 1 equal to dz upon psi 1 a1, which can be easily integrated to obtain z is equal to x psi 1 a1 plus b1, where b1 will be constant of integration, and it must be function of our constant of integration a1, right? So where psi 2 is another arbitrary function, right, of our arbitrary constant a1, right? So finally we arrive at z is equal to x psi a1 psi 1 a1 plus psi 2 a1, and by replacing value of a1 and an a2 we obtain solution z is equal to x psi 1 y plus lambda x plus psi 2 y plus lambda x, and we can combine this solution with the other solutions corresponding to lambda 3, lambda 4, and so on, lambda n, to arrive at a final complementary function like this, like z is equal to x psi 1 y plus lambda x plus lambda 2 y lambda x plus phi 3 y plus lambda 3x, and so on, phi and y lambda n plus x. As we can see that here new factor has been introduced because of the multiplicity of the root of auxiliary equation. So this case number 2 can be generalized for root of any multiplicity, that is of multiplicity 3, 4, 5, and so on.